In this video, I'm going to be speaking about standing waves. It's part of topic 4.5 of the IB Physics Syllabus. That means it's an SL and it's also of interest to HL students as well. Please take a moment to read the success criteria for this video. Before we can talk about what standing waves are, we need to cover what superposition of waves mean. In this first diagram, you see here I've got a pulse. It just means I only have part of a wave, and it's moving to the left. Likewise, I have another one right here moving to the right. So let's think about what this pulse is doing. As it's moving down the string, it's disturbing it, and it's causing it to raise up this amount. Let's call that a +1. Now the superposition means that when we get to this spot, in other words, when this pulse reaches this one, we end up getting a vector addition, which means both of them are trying to pull the string up +1, and that causes, when they meet in the center, to be pulled up +2. Notice that as they move away, it goes back to as if they weren't doing anything at all. Now these two pictures came from an animation created by Dimitri, and I'll put this link in my comments. Now what I've got is a picture of what he has for his animation, and he's trying to show this idea of superposition. This red wave is moving to the left. At the same time, this blue wave is moving to the right. Now, you can see the black, which is the vector sum of these two waves. And looking at the picture here on the left, you can see that at this position, the blue wave is pulling it up, and so is the red. So when that combines, I'm going to get like a super crest, or here, almost like a super trough. In this example, since they're both pulling at the same direction, whether it be up or here they're both pulling down, and we get an amplitude bigger than either of the two amplitudes to begin with, this means we have constructive interference. Now let's look at the picture on the right. What we have here is just a little bit longer, so you can see that our waves, red one moving to the right, blue one moving to the left. Now, instead of us having it lined up so that we have two crests at the same time, now I have a crest appearing at the same place as a trough. Well, if this is trying to pull this up one and the blue is trying to pull down one, my net result is basically nothing. We would call this destructive interference. That means my net vector sum is going to be less than either the amplitudes that I had to begin with. So if I was to create a standing wave and draw it, a lot of the times you see something that looks like this. And what we have are two traveling waves, one in this direction, one in this direction. And I'm going to have then places where I have destructive interference or constructive interference always occurring. Sometimes they constructively to the top and sometimes they constructively to the bottom. That's what the dotted line's all about. We call this place here of destructive interference a node, and this place here an antinode. Remember, a traveling wave, let me draw a transverse one because it's a little easier. That should look like a sine wave. So let's compare these then. Our standing waves, those are two traveling waves traveling in opposite directions that are always going to give us these constructive and destructive interference pattern. Though with the traveling wave, let's say it was moving to the right, all points eventually, so if I put a little bit time later, all points eventually will reach the maximum. So we usually talk about traveling waves having an amplitude and standing waves having a maximum displacement because not all points are going to reach that. If I say this is our equilibrium line, in other words, where the medium would be without any disturbance, here at the antinode, you can see we've got a lot of change, where we get no change here at the note. Though, on the traveling waves, all parts of the waves will eventually hit the amplitude. We also know that traveling waves, they transfer energy. Standing waves do not. And one last thing, if I put a little marker P there, that point in both of these cases, because I have a traveling wave which is transverse, it goes up and down. Same here. Both of those points will actually exhibit simple harmonic motion. Don't get this confused with the speed of the wave. The speed of the wave is how fast in a traveling wave the energy is being transmitted, whereas the point P is moving perpendicular to that in my transverse wave here, and it actually is going to speed up, slow down, back and forth. There's another thing we need to consider, and that's what happens to the wave when it reaches the end. On the left here, I have something called a fixed end. In other words, when my pulse moves down here, it's being held tightly. So the pulse is going to be trying to pull this up. With Newton's third law, we know that there is an equal and opposite reaction. And since this post here isn't moving anywhere, what ends up happening is the wave will then be inverted and then move backwards. We can say it undergoes a phase change of pi. But on this side, we call it a free end, or sometimes we call it an open end. And what's going to happen here is when it gets to this end, because this is allowed to move up and down, we're no longer going to get that Newton's third law causing a force on it. And what happens? Well, it does get reflected, but notice there is no phase inversion. If it goes in as a peak, it comes out as a peak. When we had a fixed end, when it came in as a peak, it comes out as a trough. So let's apply this now to strings, clarinets, and flutes. I use these as examples of musical instruments that many people think of. A lot of times instead of saying string, I'll actually say guitar. So with the guitar and the string, one end, let's say here, is going to be at the bridge, and this side, maybe it's your finger pushing down on one of the frets. What that does create is a fixed end at each side. The lowest frequency or the longest wavelength I'll be able to create in this string will look like this. On its reflection, it will be down here. Notice that this is actually 1/2 of a wavelength. If I did this, there would be one full wavelength. If I called this string length L, that means I would need 2L to equal 1 lambda. So now let's look at the clarinet. This is going to be a little different. Let's assume that over here, this is your mouth. Since the air is kind of trapped on this side, right here, we're going to have a fixed end. Now, this is the end where the horn flares out. You might say, well, there is no boundary there. Well, the air does go from being contained inside the column to being free. So we actually will get a reflection here. But this is going to be an open or free end. Now, if it's going to be an open end, remember, if it came in as a trough, it has to come out as a trough. Or came in as a crest, we'd have to have it leave as a crest. What that means is I need to have an antinode. And if I drew this in, so let's think about that. How much is going to be one complete wavelength? Well, I have really just a quarter of a wavelength here. It has to come back to the center and down to the bottom and then up again. This means that I'm going to have lambda equals 4L for the first time I can get this wavelength, the standing wave, to occur. Notice that I have to meet these boundary conditions. So one of the things about standing waves is they're going to only happen at certain wavelengths or certain frequencies, whereas traveling waves, it can be at any continuous value. All right, now one last thing, applying to a flute. You don't actually wrap your lips around a flute. You blow across it, which means I'm actually going to need an antinode at both ends. The longest wavelength, or the lowest frequency, is then going to be and here we have lambda is going to equal 2L, just like the first one. If I continue this on, I go from a crest down to a trough, back up to a crest. The other thing to notice here is that the string and the flute end up getting the same kind of properties. It's more important that the boundary conditions are the same, which is why they're going to give us same results, than it is the actual makeup, or whether it's an antinode or a node. So let's go back to the guitar, the string, for a second. Let's talk about the next possible one. If we call the first one I've got here drawn the first harmonic, I want to be able to draw the second harmonic. Well, notice I've got 2 nodes. The next one's going to occur when I have 3 nodes. And if I draw that one in, notice now that my wavelength is actually the length of the string. Now we know V equals F lambda. That's our wave equation. And the speed of the wave is actually dependent on the medium, not its frequency or wavelength. So in this case, if I look at the very first one, if I say the frequency of the first one times the wavelength I have in the first case, it's going to have to equal the frequency in the second case times the wavelength in the second case. Let me substitute in our values for the wavelengths. Frequency 1 is going to be times 2L. Frequency 2 is going to be just L. And let's do some rearranging here. Let's cancel out these L's. And we have that the second frequency is actually 2 times the first one. At this point, what I want you to do is stop and pause the video. Go and try and draw the next 2 possible wavelengths. To help you out, the next one should have 4 nodes. The one after that should have 5 nodes. I'm going to do the easy one first. In this case, you can see that I've got 2 wavelengths. So two lambda is 1L, or lambda equals L over 2. Now in this case, I have 1.5 wavelengths. And I have to write this one down because I tend to mess it up. So I've got 3 over 2 wavelengths is L. So that means that my wavelength is going to be 2/3 of a wavelength. Or if you take this entire distance here, which is L, break it into 3 parts, 2 of which will give you 1 wavelength. Now, I'm not going to take the time to go through this, but just like I did for the first 2 frequencies, this one's going to be 3 times the fundamental frequency, or the first harmonic, and this will be 4 times. Remember I said the flute and the guitar or the string are going to be exactly the same? We actually will be able to do the same thing here. So pause the video and see if you can draw the first 4. Now, to be honest, when I draw these, I do start with the nodes. If you take a look, the flute, the first one had 1 node. Now I have 2, 3, and 4. And then I draw my wave according to the quarters like we've done before. I'm going to have to start here at the open with an antinode to my node. And I need a node at each one of those dots. If we worked our way through, we'll get the same idea in terms of the fundamental frequencies, this one being F1. This will be 2 times that, 3 times that one, and 4. Now, where things get a little bit more interesting is in the clarinet. I need to take off some of these diagrams so I've got space to write. So let's think about the next one I'm going to need. I'm going to need to keep a node here. I'm going to add one more node, and I have to finish with an antinode because it's an open part. Okay, so let's go through one more time. How much of a wavelength do I have? Well, I have 3/4 of one wavelength in my length L, L being the length of my pipe here. So that means my lambda is going to be 4/3. Let's work through in terms of our speeds and our wavelengths. So F1 lambda 1 should be equal to, let's call this 2 for now, F2 lambda 2. It was 4L, and now I've got 4/3 length. So if I move this around, I'm going to have now that F2 is actually 3 times F1. So what ends up happening with a clarinet is that the next possible one is 3 times F1. And if I do the next one, what I actually end up with, and you can go through, you see my picture there, and you can do the math, you end up getting that this one, I'll call it 3 for now, ends up being 5 times the first harmonic, the first possible frequency. So in some cases, people say that this one's actually missing some. So when I go from the first one at F1, the next one actually gives me 3F1, 5F1, 7F1. We're missing the even number multiples of the frequency. So I've gone back and I've drawn in the first 3 here. Again, remember when I go down from the first one, I'm just adding one more node, making sure I have the right boundary conditions, and then I can figure it out. I know some people go through and say, oh, well, we have a series or sequence for all of these. Yes, it's true, but to be honest, my brain is full of enough things to memorize. I don't say that you should go and memorize those formulas. They are not in the data booklet. What I do recommend is you to be able to figure out where I'm going to have antinodes and nodes, be able to draw these diagrams here, and remember, how did I get those frequencies? It's because the velocity is constant, because our medium's the same. I would do that and then apply it to your different situations rather than memorizing an equation and perhaps using it in the wrong situation. So let's put these in a couple different examples before we finish the video. Here we go. We've got a standing wave created in a string, and we can look, we've got a fixed end at both ends, and we've got one more node in the center. So this is not the first harmonic, this is the second one. So what is P? P is going to be a node. It's not changing its amplitude or its displacement there at all. And X, well, if I go from one end, I have one complete wave. Remember, a lot of the times with questions like this, it's easier to answer it column by column, and then when you're done, you can see which one has not been crossed off. Okay, it gives me 4 different organ pipes, and notice we have open ends and closed ends, and it wants you to set up the first harmonic inside each pipe. So let me just go and draw those in. So with two open ends, I need antinodes at each end, and it will have one node in the center, and this is actually 1/2 of a wavelength. With B, I have a node at the beginning, an antinode at the end. This is actually just showing 1/4 of a wavelength. Now, you can also think of it as in terms of this is what L equals, the length of my pipe. Another way to think about that is that lambda has to be equal to twice the wavelength or the length of the pipe. And here it would be 4 times as long. Now let's just double check. What is it we're looking for again? We are looking for the pipe with the fundamental note with the lowest frequency. Remember, lowest frequency, that would equal the greatest wavelength. So first of all, we can see here that's definitely not going to be A. We can strike that off. Now, again here in D, let's look at it first. I have 1/2 a wavelength, but this is twice as long. So I'm going to say 2 times L, because L was the length of the shorter pipe, is 1/2 of a wavelength. So that means lambda is 4L. Well, that's the same answer as B. So odds are if B and D are the same, they're not going to be the right answer. Let's just double check with C. We've got 2L equals 1/4 of a wavelength. That gives me that lambda is going to be equal to 8L. That definitely is the greatest wavelength. It will give us the lowest frequency. And finally, let's do one with some numbers. We have 2 pipes, Q and P, and notice that they're drawn here. One has 2 open ends and one has an open and a closed end. We are looking for the first harmonic, and this is looking for the best estimate because remember, the IB, you don't get a calculator for the multiple choice questions. Let's start by drawing in the first harmonics in both our pipes. Pause the video and try it yourself first. Okay, so I hope you got that. And if we think about them being the same length, for P, I've got lambda, that should be like a subscript P divided by 4, because that's 1/4 of that wavelength, whereas in Q, it's 1/2. Let's move that around. Lambda P is going to be 4L, and lambda Q is going to be 2L. If I use my wave equation, because we know that they're going to have the same speed, because it's the speed of sound in the same medium, I'm going to have Fp lambda P is going to equal Fq lambda Q. If we substitute in our known values, 220 is the frequency in P, and its wavelength is 4L. In Q, we have the frequency of Q we're looking for, and its wavelength is 2L. And if I move that around, we are going to get that we're going to have 220 times 4 divided by 2 gives us 440. Now let's see if we can logic through that as well. In this case, our wavelength has decreased by 1/2. And since frequency and wavelengths are inverse, if my wavelength went down by 1/2, my frequency should go up by 2. Okay, so that takes us to the end of the video. Please read through the success criteria one more time, and I hope you can say yes to all of these I can't statements.